Section 3 is kinetic energy. And really, the next several sections, we're just going to go through all of the different varieties of energy. So we're starting off with kinetic. Kinetic energy is the energy of motion. So we have translational kinetic energy and rotational kinetic energy. The energy of an object in motion along a line is translational. If you remember from geometry, translating an object is moving it left and right or up and down. Kind of the same idea here. So we're just moving along a line. Rotational kinetic energy is that of an object rotating about a fixed axis. So that's like when we're spinning. So translational first. If we consider a car being towed with a tow rope, with a constant force F and displacement D, so that the force does work, W equals FD, on the car. So ignoring friction and drag, this work is transferred into the car's energy of motion, and that is kinetic energy. So by the work energy equation, this is given by W equals delta K. So that would be kinetic final minus kinetic initial. Remember the work energy equation. We're going to be referencing that all the time. So from kinematics, we know that V final squared equals V initial squared plus 2 times acceleration times delta x. And so from that, with the work energy equation that we have up top there, we also know that delta x is the same as d, and acceleration equals F over m. So we can rewrite our kinematics equation as V final squared equals V initial squared plus, and then 2 times force times distance divided by mass. Now, force times distance is work, so that turns into VI squared plus 2 times work divided by mass. So then, if we solve that equation for work, we can have two different versions of this equation. We have this one. It's really the same thing twice. We just have 1/2 times mass times velocity final squared minus velocity initial squared. Or we can distribute the 1/2 mass. And we wind up with 1/2 mv final squared minus 1/2 mv initial squared. Now, if we compare what we just wrote, this one here, to the original work energy equation, then we can see that kinetic energy final must be 1/2 mv final squared, and kinetic energy initial must be 1/2 mv initial squared. Or in other words, kinetic energy is actually just 1/2 mv squared, which is great. That's our equation for kinetic energy.
A car going 60 miles per hour.
Yeah, so now we have some approximate kinetic energies. We have an ant walking. The kinetic energy is 10 to the negative 8th joules. A coin dropped from 1 meter would have 5 times 10 to the negative 3rd joules. Person walking, 70 joules. A fastball at 100 miles an hour, 150 joules. A bullet, 5,000 joules. A car at 60 miles an hour, 5 times 10 to the 5th joules. A super tanker. What's a super tanker?
A tank.
No.
Semi.
No.
A boat.
A boat.
That's a super.
Like the boat that ran into
The bridge.
the bridge, except not quite. That was a cargo ship, but that's the idea. It's one of these gigantic freighters that holds
And by the way, Steve,
oil.
what would be worse, getting hit at 60 miles an hour or getting shot?
Getting shot.
All right. So finding the work to set a boat in motion. So at a history center, an old canal boat is pulled by 2 draft horses. It doesn't take much for us to keep the boat moving. The drag is quite small, but it takes some work to get the 55,000 kilogram boat up to speed. The horses can pull with a steady force and put a 1,400 Newton tension in the rope that connects the boat. The rope is straight and level. The boat starts from rest, and the horses pull steadily as they begin their walk down the tow path. How much distance do the horses cover as they bring the boat up to its final speed of 0.7 meters per second?
So what is this?
What is what?
A canal boat.
A canal boat?
Yeah.
A boat in a canal.
Well, why are horses pulling the boat?
So people don't have to pull it.
Because they're in a canal, and the horses can walk alongside and pull the boat.
Mm-hmm.
So what we're going to do is we're going to draw a picture. So we have this boat, and what's it look like?
Yeah.
Looks like that. Exactly like a canal boat. And then later, exactly the same boat. And so then we have a distance that the boat has gone. And what else do we know?
We know its weight.
It's sped up.
It's being pulled in this direction with a tension. And here, same thing, tension. All right. What else we know?
Velocity initial, velocity final.
We don't know its weight, but we do know its mass. 55,000 kilograms. What else do we know?
The final speed.
Okay, so VF 0.70 meters per second. What else do we know?
VI equals 0.
Okay, good.
Tension equals 140 or 14,000, I should say.
1,400.
14,000.
1,400 newtons. And what else? D equals, don't know. All right. So what do we do?
Set up one of them fancy dancy equations.
Set up one of them
They
equations.
don't look very fancy.
Here's what we know. The change in kinetic energy is equal to the work done. Kinetic energy, delta K, is equal to Kf minus Ki, but Ki will be zero because it wasn't moving in the first place. So it'll just be Kf, right?
So 1/2 times mass velocity final squared.
Good. And what about the work?
The work
Is
is equal to that. So then we can do
Work is force times distance.
Yeah.
The force in this case is,
1,400.
but it's what letter? So
T in this case.
T in this case times the distance.
so divide.
Yeah, so solve for distance, right? So we'll divide both sides by T. So the 2 is in the denominator. The T will be in the denominator. So we have D equals mv VF squared over 2T. Okay, now we can just plug everything in. So M, 55,000 kilograms. V final, 0.70 meters per second. This is squared. Divide by 2 times the tension in the rope, 1,400 newtons. Okay, what's a newton?
Meters per second.
Kilograms,
Kilograms.
meters
Yeah.
per second squared. So the kilograms will be gone.
And then the second square.
And the meters.
The meters up top will be squared.
So you can have
The
second
meters on the
squared
bottom will be gone.
Yeah, the second squared on bottom and top are going to be gone because you're squaring.
The second squared on the bottom, the per second squared on the top with the per second squared on the bottom will be gone. And the meters squared on top with the meters on the bottom will leave us with just meters. Good. Okay, so what does this work out to?
9.6.
9.6 meters. So it takes these horses 9.6 meters to get it up to a speed of 0.7 meters per second.
It's not that bad,
Not bad.
especially for how heavy that boat is.
Horses are strong.
Hey.
Or you just get a vehicle that has horses contained in 350 cubic inches.
Maybe. Okay, rank in order from greatest to least the kinetic energies of the sliding pucks. What should we do?
Write down that equation.
What equation?
1/2 times mass times velocity squared.
Okay, you guys are catching on. 1/2 mv squared. Okay, how does this help us?
Well, if we know that the mass, we just can kind of plug everything in. The velocity is going to be the most important part.
Velocity is the most important. Yep.
So B is probably going to be first because the velocity is being squared.
Times 0.5. So 4.5.
So yeah, 9 times 1, but half of that, so
The other one's
4.5.
4. D is 4. D is 4. Because 4 times 1 is 4.
Okay.
And
A is going to be 2. And the other one's going to be -2.
then
The velocity is squared.
Oh, so it'll be 2 again.
2.
Yep.
So B is greater than D is greater than C is equal to A. C.
A and C are the same,
Yeah.
so it doesn't matter how I write those. Good. Use the equation. All right, so that was translational. So now we switch to rotational. The blades of the turbine. We've talked about the turbines before, right?
Yeah, and my dad didn't believe me when I told him how fast they're going.
Yeah, they're going. How fast are they going?
For like 200 and some miles.
100 miles an hour.
Is it 100?
It's 100, yeah.
I thought it was 200.
Well, then you told them the wrong thing. Every time I see those, I time them. I let them go around 10 times, and I time how long it takes to go 10. And then I just kind of do some quick math in my head. I'm like, yep, about 100 miles an hour. It's amazing.
Well, how long are they?
50 meters, I think.
Yeah,
All of them? It's like uniform?
pretty uniform. All right, so although the blades have no overall translational motion, which means they're not moving from left to right, every part of the blade is moving, so they must have kinetic energy. So that's rotational kinetic energy. So remember that everything on a rotating object turns with angular velocity. Our symbol is, what is that?
Omega.
Omega. And with a circle of radius r means any particle on that object has velocity. Here's our equation for that. V equals omega r. So therefore, particle one is here. Moves with the speed v1 equals r1 omega. and so has kinetic energy. 1/2 m1 v1 squared equals 1/2 m1 r1 squared omega squared. Particle 2 has kinetic energy found the same way. So the object's kinetic energy is the sum of the kinetic energies of all of the particles. So what we're going to do is K rot. So that's K rotational energy. The kinetic energy in a rotating body is 1/2 m1 r1 squared omega squared plus 1/2 m2 r2 squared omega squared plus, and so on, equals 1/2 times the sum of all of the masses times all of the radii squared omega squared. Omega is constant for the object. We just have to add up all their masses times all of the radii squared. There must be a better way to do this, though.
You think?
I
Yeah,
hope so.
you would think. Having been through this class for this long, you should know. That term in parentheses should look familiar. It's our buddy. We did this already. It's moment of inertia. So we have a simpler formula for rotational kinetic energy, which we rejoice about because that would have been a bummer to have to add up an infinite number of little masses. So K, the rotational kinetic energy, is 1/2 times the moment of inertia times omega squared. This is not a new form of energy. It's the same as kinetic energy for motion, but it's in a form that's convenient for rotational motion. So we compare this formula with the other one for kinetic energy. It's 1/2 mv squared, and we see that they're the same. We just have to remember that moment of inertia is the rotational equivalent for mass. So we have a rolling object like a wheel. It's undergoing both rotational and translational motions. So remember that the wheel is both moving in a straight line and turning at the same time. So it has both rotational and translational motion. So therefore, its total kinetic energy is a sum of rotational and translational kinetic energies. So we would have this situation for that case, for like a rolling wheel. Translational and rotational. 1/2 mv squared plus 1/2 I omega squared. So the kinetic energy of a rolling object is always greater than the kinetic energy of a non-rotating object moving at the same speed.
Seems important.
It is important.
I should write that down on this view.
Big concept there. All right, so anytime a cyclist stops, it will take energy to get moving again. You've all ridden a bike before. I think so. Using less energy to get going means more energy is available to go farther or go faster. So racing cyclists want their bikes to be as light as possible. It's particularly important to have lightweight wheels, as this example is about to show. So consider two bikes that have the same total mass. So the bikes have the same mass, okay? The question is, where should we put the mass? So different mass wheels. Bike 1 has a 10 kilogram frame and two 1 kilogram wheels. Bike 2 has a 9 kilogram frame and two 1.5 kilogram wheels. Both bikes, therefore, have the same 12 kilogram total mass. What is the kinetic energy of each bike when they are moving at 12 meters per second? Most of the weight of the tire and wheel is at the rim, so we can model each wheel as a hoop. Okay, so I'm going to split this into bike 1
Bike 1 is better.
and bike 2.
We're looking for greater joules, right?
Well, it says, what is the kinetic energy of each bike when they are moving at 12 meters per second? So, bike 1, we have kinetic energy of the wheel, which is
Translating and rotating.
translating and rotating. We also have kinetic energy of the bike,
Which is just
which would be the total situation. Okay, so kinetic energy of the wheel. So the kinetic energy of the wheel will be, we have to figure out 1/2 I omega squared, the inertial, what am I trying to say? The moment of inertia times,
2 pi.
okay, then plus 1/2 mv squared, because it's rotating and translating.
Oh, hey.
So
I got this out for a reason.
that is 1/2 what? What's I?
It's
It is 1/3 times m times l squared.
No.
No, wait. It's an r squared.
Mr squared? Yep. Okay, and then we still have omega squared. What's omega going to be?
2 pi.
No.
Isn't that supposed to be 1/2 times 1/3 mr squared?
No,
Mr squared.
It's just mr squared.
it says it right there. I was reading the wrong.
Oh, okay.
It was on the opposite side.
How do we calculate omega?
wait.
I should know this.
Angular
2
acceleration
pi.
or angular velocity equals.
Whatever it is, it'll be squared.
Omega equals 2 pi radians over t.
No. Well, maybe, but that's not what we want here.
Delta t over delta t.
Definitely not.
Velocity time or velocity over the radius.
Yes. V over R.
Woo.
Okay. Then plus 1/2 mv squared. Okay, so we can live with that for now. And the reason I wanted that one is because everything is in terms of velocity and radius and mass. Okay? Now, the kinetic energy of the bike. We'll need the kinetic energy of the frame and the wheel.
It's equal to k root plus 1/2 mv squared.
Wheels.
Does
So,
the R divide out here?
yeah, we'll simplify in a minute. So, the kinetic energy of the frame would be 1/2 the mass of the frame times v squared plus
2 times.
the wheels. There's 2 of them, so it's going to be 2 times
1/2
all that stuff, right? Because that's just what for one wheel. So 2 times. Now, the initial stuff right here, this stuff is 1/2
See, we don't know the radius of the wheel though.
Do we need to?
No, because the m over there is being on top, not on the bottom. So those don't work out.
What happens there is what I'm asking.
1/2 times. It's a fancy one. 1/2 times 2 is 1.
No, but I'm not distributing that 2 yet.
The r squared on top and the r squared on the bottom.
Right. That winds up
Yeah.
being r squared over r squared. So the r's are gone. So we just have the mass So I'm going to write mass of, I don't want to get confused with the mass of the frame. So this is mass of the wheel times the velocity squared. Then plus 1/2. Again, this is the mass of the wheel. Velocity squared. Okay, now I'm going to simplify this. So K bike equals, I can't simplify this first term, so I have 1/2 mass frame v squared. Now, if you notice inside the parentheses, 1/2 mass of the wheel v squared plus 1/2 mass of the wheel v squared
Just gets you to
1
is really just mass of the wheel v squared
times 2.
times 2. So I'm going to have plus 2 mass of the wheel v squared.
Wait a second. When you distribute the 2, it goes once into each, right? Oh yeah, never mind.
Those are like terms.
Yeah.
Okay. So we know the mass of the frame and we know the mass of the wheel actually in both cases. And we know the velocity. We know everything we need to know, right? So this formula applies to both bike 1 and bike 2,
Just with different masses.
just with different numbers. So at this point, we can plug in these numbers to find the kinetic energy of the total bike for both bike 1 and bike 2. So bike 1, plug in the numbers, and bike 2, we'll plug in the numbers. The question is, what do we get?
1/2 times 10
Is 5.
times
144.
12 squared.
5 times 144 is
Could probably use a calculator.
okay.
So what'd you get for bike 1?
1008.
1008. And what's the unit?
Joules.
Joules. And what'd you get for bike 2?
1080.
1080
Yeah.
joules. Okay. So then, which one's better?
Bike 1.
Because it makes less.
Yeah, because it
energy
makes
to
less.
start.
And let's see. It will take energy to get moving again.
We calculated the amount of energy it takes to get moving, so bike 1's going to be greater. Or better, I should say, not greater.
Yeah, bike 1's better.
So you're saying bike 1 is better? How come bike 1 would be better?
Because, like you said, the velocity or the weight of the wheels has the energy of the wheels is going to be greater than the energy of the what was it?
The difference here is the weight or the mass of the wheels. So bike 1 has lighter, less mass in the wheels, so that equals lighter weight wheels. And notice that bike 1 results in less kinetic energy required to get the bike moving, basically.
It's
Okay?
crazy how big the difference is in half a kilogram.
Yeah. So racing cyclists will want lighter weight wheels because it's easier to get the bike going.
And
Okay.
bikes don't actually weigh that heavy, do they? 20 pounds?
These are pretty realistic problems, so it wouldn't surprise me if that's what they weighed.
I
But
thought they got lighter than that.
if everything else is equal, like if you're required to have a total mass of your bike to be a certain amount, like this problem required, then you would want your frame to take up that weight as opposed to your wheels. You want your wheels to weigh as little as possible for exactly this reason, because of the requirement to spin up the kinetic energy is less, even though it's, 1080 versus 1008, it is still more energy used to get it going as opposed to the other one. You'll have an advantage getting off the line as opposed to somebody else.
So you're saying if I took like argon and filled someone's tires full of argon, they would go slower,
Because argon is
heavier
than
air.
air.
Yeah. Or like mercury or something.
Mercury, yeah. Definitely put mercury in your tires if you want to go slower. Okay, is that it? Yep, we're done.